Welcome back. So let's work in our next tutorial. So in this case, we're going to do a little bit adaptive mesh refinement. If you recall, we did it in 2D. Now we're going to do it in 3D. Pretty much the same, but I just want to show you something in additional post-processing and some additional steps. So I will pick up one geometry, one solution. For no reason, I picking this one with the polyhedral cells, okay, but you can work with that or whatever, it doesn't matter. So the first thing, I hope you remember the steps for adaptive mesh refinement. But before doing that, we need to identify a region where we want to refine. Now, so let me hide this, and this plane. Okay, so we have this. So we can create isosurfaces. You go here in Resolve Surfaces, see that you have multiple options, and you have isosurfaces. So these represent the regions that have the same value. So let's say that from zone. So this zone is the whole domain, and I want to create an isosurface of what? Temperature. Okay. And I want compute, it will give you the minimum and maximum. I want the isosurfaces that have 25 degrees. So see here how the influence. So this is isosurfaces. So here you can use this. It's useful for post-processing, sure, but also for selecting the cells where you want to apply that mesh refinement, okay? So see here that, let me move here, different values, so you can also use it with different quantities. So velocity, for instance, the regions where you have, let's say, where I have the largest velocity, and you have it there, okay? Or you can go and let me go Y, velocity, Y component, compute, and I want negative regions. So there are negative values where I don't see it here. So see here that kind of this is telling you where you have recirculation, where you see the negative value. Okay, so you can identify regions there. So there are many stuff that you can do here. So let me put here. So see that all these regions you have negative values. You have the recirculation also here. Okay. So for our proposals, let me go back and let me put it 25 here. Okay, so compute 25. Okay, you need to move it manually. I don't know why it doesn't take it. So you can create also multiple surfaces, all 25 here, you can put more surfaces. So see that I will select all these surfaces there. So create, and you have the surfaces there. So you have something also here called isoclip. It's pretty much the same, but it will clip all these cells. So here you're clipping the surface. In this case, you start to do clipping in cells or all surfaces as well. So it's very similar. So let me go here and here, and let me clip in everything actually, and compute, and well, you already have the clip there, so we should apply that one somewhere else. So in any case, you have the idea how it works. Okay, so if I go back here, see that you can access that isosurface and you have it there. Okay, so let me deselect that one and put it here, your isosurface, and I want to color that isosurface using, for instance, velocity magnitude. Okay, see there that you have it. And I don't want to use global values, I want to use the local values. Okay, so this is the local velocity knowing that isosurface. And then you can go here in the scene here, and you can add that contour also, and see that you have, let me hide the pass lines. I don't want the pass lines. So you have all this there. So in any case, we identify this region here, and we want to add more cells there. Okay. So remember that the adaptive mesh refinements here, cell registers, new, and you have different fields. You can add it to the boundary layer. Okay. You have many options. So we want to go here, field variable. I want to use temperature. Okay. And here you choose values. Let's choose values that cells in range, compute. So I want to have cells, I know, within 22 and 30 Celsius. Okay, save displays, and see here that it's showing you all cells marking. So it works pretty much very similar to the previous within 2D. So it's up to you to choose. So in this case, for me, I'm happy with this. Okay, you have your register there, and now you can go here, refine, and this is a little bit expensive, it's heavy. Okay, so see that now it refined the cells. Okay, it add almost 100,000 cells more. Okay, so you go into cell count, see that now you have 200,000 cells. Previously it was almost 100,000 cells. So as you go here, see that now you see the splitting. Okay, so it's doing the splitting of the cells. Let me put it in this cut plane here. Okay, let me go here, like it. And see here that it's splitting cells. Okay, so it's up to you to choose that sizing, no, the region where you're applying that. But here I think also you got the idea that, see also that it affected the boundary layer, that your mesh can grow really fast, the cell count. Okay, in 2D it wasn't that big, but in 3D you start to see that this will grow really fast. So this is something that my advice, again, do not abuse it. Okay, it's better that if you have shockwave that you want to refine, or regions like this one that you want to capture better the interface between the hot and cold interface, maybe yeah, you can do it, but for the boundary layer, don't use adaptive mesh refinement. Better go back to the meshing stage. So let's rerun this case. Okay, well, I don't need to rerun, just start from this solution. So when you go here, you press, let's run just 100 iterations. You press calculate. It will interpolate the solution to the new mesh, and then it will start from the previous solution. So see that you always will see this jump. Okay, this you find that it's just interpolated to the new mesh, and now is here you are computing in the new mesh. Okay, so you're going to have all these oscillations. Okay, and see that the convergence now since gets slower, not twice the number of cells, but it still is a nice convergence rate. It should converge also relatively fast. So see that mass flow is the imbalance is almost zero. Here mass weight average at the outlet. There are some oscillation, but it's also stabilizing. And the Y plus, see that increase a little bit. Okay, here. This is strange, it should have reduced, but probably you need to let it run, it will go down. Actually, see that it's now going down. Okay, and I think, yeah, it will converge soon. So it will arrive to the convergence here, to the tolerance of the absolute residuals here. But this monitor that we impose here is still, you haven't reached this one. So see that it's saving, okay, and it's almost there. So see here that it converged to the tolerance. Solution converges to the tolerance of the monitor. But remember that you put here another, should be, was, okay, also converges to the other monitor, this one. So you have, here we have these two monitors. This one residuals, 10 to the minus 3, you see here there. And then you have the other one, this converge condition. So in this case, it converges first to this one, but then you need to fulfill also the other criterion. Okay, so it took a little bit longer, but we have a solution. So now we can also do the post-processing. Okay, so pretty much same, just nothing should change. Probably we get better results now, finer mesh. Okay, that is the hope. No, now finer mesh will give you better results. Okay, and let me go here. Okay, and probably if you compare the previous one and this one, you will see that also the isosurfaces are better resolved. Okay, so I can draw the mesh there just to see. Okay, show me the edges. Okay. So you can see the edges, they're projected. This is the projection in the isosurface. Okay, and this is one you can do, go ahead and do a second, okay, a second refinement cycle. It's up to you. So for instance, let me go back. Okay, let me see another. Okay, so for instance, you can go like this, oops. close. So you can go again, second cycle. So you have it, here, second, or you can use different criteria. Okay, you have the boundaries, residuals, volume. So it's up to you. So I think we covered a lot in these 4 tutorials. Okay, these are the 4 first tutorials. Okay, so it seems to be simple geometries, but you see that we have covered a lot, from geometry generation, mesh generation, to setting the case, and also post-processing turbulence quantity. Important, I think, also you have realized that your mesh depends on the turbulence quantity. So it's important to have an idea of those initial turbulence estimates that can tell you a lot. So later we're going to go in another tutorials and we're going to see how to compute integral length scales using the turbulence quantities. So we know that we can use a combination of k epsilon, k omega, whatever, to get an idea and then do some meshes just focused to those quantities. Now, using those quantities. So that is called a precursor simulation. So that we'll start to do that in starting from tutorial 7, 8, but then we have another tutorial. Okay, so now everything that also we have done so far is steady. So the next one, we're going to do a tutorial but on steady. Okay, so simple, we go back to 2D. Okay, so you have seen 2D, 3D, nothing changed. Okay, the difference is memory consumption. So we go back to 2D, but let's see the classical cylinders case, now the von Karman Street, and how to run this case on a steady regime. So that's all for this case. Thank you for your attention and see you in the next tutorial. Bye.